Okay, so today's 5/29/25, and Thursday we're going to do some stuff on wave reflections and standing waves. So the video recording today should hopefully suffice in the event that you're having to watch this from home. All right, guys, waves can do some things that particles cannot. They reflect differently. Let's see, Odin, I'm going to try to throw a particle to you, but I'm going to reflect off of this wall. So the question for you is, will you turn and tell that person that you're sitting next to, do I have your attention? No, get the phone book closed. Come on, guys, get those things closed up. Come on. Say goodbye to it. Wait, you didn't say goodbye yet. Say goodbye. You're probably watching some sort of game. I get thinking. All right, will you turn and tell that person that you're sitting next to which of these equation things I should hit if I want to reflect this tennis ball off the wall to go to Odin? So where should I do it? Should I hit the electricity and circuits? Should I hit the reflection, refraction, optics? Should I hit the SHM and waves? Should I hit the momentum impulse? Should I hit the work and energy? Where should I throw this thing to be able to get this particle to reflect between me and Odin? I want to hit Odin with this thing. Where should I throw this thing? Someone take a guess for me. Where should I throw it? Which one of these things should I hit? The momentum and impulse? Okay. So thank you for trying. No. So we're going to try it. I'm going to try to hit that wall. I'm going to reflect it to you. Are you ready? Okay. Now, thank you. All right. Throw it back. Oh, no. You're supposed to reflect it back. All right. Now, where should I hit? Momentum and impulse got it close, but it looked like it overshot them a little bit. Where should I go for particle? Raise your hand if you've ever done any billiards or something like that. Particles obey a law of reflection, that the angle of incidence is equal to the angle of reflection. I really should go halfway between he and I, so that therefore the angle coming in would equal the angle going out. It'd be more like the SHM and waves, and that's about halfway distant between he and I. Okay, so we're going to try that again. Are you ready? Okay, so off the wall, and so sure enough, goes right to you. Hit it off the wall. Okay, pretty good. So particles reflect very consistently, right? Obey a law of reflection. Now, if I wanted to get this thing to, let's see, if I wanted to get this thing to Gundy, what's going to have to be different about this? I'm going to have to throw harder. Now, roughly the same angle. Are you ready? Okay, I'm going to try it. So hopefully I don't hit the window. All right, Gundy, you ready? Okay, not bad. Throw it back. Okay, now the angle is off a little bit there, but the idea there is that I have to be able to. Nice try. All right, thank you. Hope you throw that thing to me. Reflect it off the ground for me. Very good. All right. Now, waves can do things that are a little bit different. So, how waves can reflect is that at a fixed end. So, if the end is fixed in place, so it could be a guitar string, it could be guitar string is probably the most common example of a fixed endpoint, is that it will reflect and it will reflect inverted. So it's going to be an out of phase relationship. So again, phase has to do with where that waveform is in its cycle. And so a fixed endpoint can reflect, but it's going to reflect out of phase. So a really good example of that is a guitar string. And a guitar string has two endpoints that are fixed. And so when you send a disturbance down that guitar string, it's going to reflect at that terminal end and reflect inverted. Now, it could also get an endpoint that is free. And an endpoint that is free means that the wave is able to ride up on the endpoint and then reflect. It's going to reflect in phase. So this would be an upright reflection. A really good example of that would be water waves at the pier. So if you've been to the Grand Haven Pier recently, you would see waves riding up the pier and then reflecting in phase. So it'd ride up along that thing and reflect back, and that would be an in-phase reflection. Now, I want to show you a couple of visuals of that. And so on the wave on a string, I think I had this thing with no end before, and I had you guys with no damping, and you saw that that would send a wave along through there. Again, I know that if I increase the frequency, I make the wavelength shorter. If I decrease the frequency, I make the wavelength longer. We've seen that. But now what we're going to do is we're going to start to do this with some endpoints that can be fixed. This is called a C-clamp, so called because it looks like a letter D. But let me send a pulse down through here. And so when I send this thing along, you're going to notice that the pulse is going to propagate along there and reflect inverted. And that's simply because the endpoints are fixed in place. Now, I can also take the endpoint and have it be a loose end. And so a loose end reflection, you'll notice that when that comes in, it's going to reflect in phase. And so particles behave a very specific way. Angle of incidence is equal to angle of reflection. Waves can reflect differently depending on the endpoints for that reflection. All right, now this is a little bit more complicated. This video here is going to show you what it looks like if I have a continuous wave going through here. And so again, you're going to see now, instead of just a single pulse, that hits that terminal endpoint and it reflects. It could be reflecting in phase or out of phase. It's hard to see that because it's continuous. Would you agree that these two waveforms are identical coming in? Each of those things, it looks like I got a little bit of a crest there, and then these are completely in phase with each other. But when they reflect, and you notice the reflection here, the reflection's sort of complicated as it moves through that, but when they return, you notice that they're now completely out of phase with each other. And so that reflection, again, has to do with what kind of endpoint we have. Now, what I want to focus in on next is what happens right when the reflected wave and the incoming wave interfere with each other. So what I'm looking for is this portion right here. And you can see what's being created there is something called a standing wave, where that wave appears to be standing still. And so the next part we need to look at today is something called a standing wave. And so that's what I'm going to try to do, slowing that motion down with a strobe light so you can sort of see that. Let's take a look at this here. If I have a confined medium, so a medium that has an endpoint to it, then we can get a standing wave can be created. And so a standing wave sort of looks like these diagrams here. These are static pictures of what a standing wave is. In reality, it's a dynamic process. It's something that's oscillating, and we'll take a snapshot of it to show that at various times. It is due to interference between the reflected wave and the incident wave. The wave appears to stand still, which is why we call it a standing wave. Each particle of the medium has a unique and fixed amount of energy, and so how we encode information in waveforms is often using standing waves. Now, Brody, would you be kind enough to help me today? You're in a good position to help. Sure. I just need you to hold the end of a slinky as I try to demonstrate this. Now, this doesn't work the best with a video recording, but we can still do this. Okay, so I'm going to have you help me with this here. Take this thing off of there so that we only use a portion of this thing. Okay, so we're just going to use a lighter weight slinky. So I'm going to have you head on down to between by Dawson there. And so Dawson, you're in a little bit of a tough spot just simply because if Brody lets this thing go, it could hit you. So if you want to get up and move out of the way, you're welcome to. Molly, you're definitely in a bad spot. And Ian, you're in a bad spot. In case this thing lets loose, I don't want you guys to get hit with this. Okay. Now, so the idea behind this is I want to show you how standing waves are created on a confined medium. First, the medium has to be confined, so it has endpoints. Now what that means is I can have a disturbance reflect between you and I. Now this is a horizontal wave, so it might be hard for people to see that as a horizontal wave, but you notice I'm sending a pulse that's toward Ryder, but it comes back towards Gundy. So you notice that your endpoint is acting as a fixed end, right? Your hand is fixed in place. The wave has to reflect out of phase. Okay, so again, it reflects like that. We could try it vertically, but then we have gravity sort of acting as well. It might be a little bit harder to be able to see that, but let's try it once. So here we go. I send you a crest that comes back as a trough and vice versa. Okay. Now, what I'm going to have you do is you try to model. You push your chair in there. Could you try to model the end being a free end instead of a fixed end? So I'm going to send you a pulse. It's going to be pointed towards Ryder. I want to see if you can have this return in phase. So it's going to come back also towards Ryder. You ready to try it? Your hand is fixed right now. Can you try to simulate a free end? Are you ready? I'm just asking you to try it. Are you ready?
Sure.
Okay, so here it goes. Okay. I know. Why don't you send? I'm going to show you what I mean by that. You send me a pulse, and I'm going to try to have my hand be a free end. So what I was trying to do is I'm going to allow it to ride with that. Okay. So you ready to try it one more time? Okay. I'm going to send it to you. Your hand is fixed in place. I want you to try to have it be a free end, which means as this pulse comes in, you move your hand with it and allow it to come back in phase. Ready? Okay, nice try. It's tough to do. Your hand is definitely fixed in place. Now, what I'm going to try to do is I'm going to try to create a standing wave. Standing waves are due to reflection between an instant and a returning wave. So I'm going to send you a pulse, and I'm going to continue to send you a pulse, but now it's going to be a continuous pulse. What I'm doing is I'm trying to add energy constructively. Yesterday, when I had you guys do this with the ladle in the bowl, what you're doing is you're adding energy to create a standing wave. You had to make sure that that energy added constructively. Now, we have our first standing wave pattern. I'm trying to create the pattern that looks like this one up here, the very first one. This is a horizontal plane. I'm going to try that now doing a vertical plane. So again, something along these lines. This is a standing wave pattern. Now, I'm going to show you this on a wave machine, and so we can see this thing with a strobe light, so you can sort of see what's happening with it. But right now, let's go ahead and try to create the second pattern that we see up there. The first pattern looks like this. The second pattern has to have would you guys agree that this is 1/2 of a full wave? If Brody and I are 3 meters apart, this would represent 1/2 of a wave, which means the wavelength of this standing wave is about 6 meters. Because I need 2 of these to be able to be a full wave. So if you and I are 3 meters apart, this wavelength is 6 meters. Now what we're going to try to do is we're going to try to get the second pattern. I'm going to have to increase the frequency. Now when I increase that frequency, you notice that now instead of it being 1/2 of a wave, how much of a wave do you see? This is a full wave. If you and I are 3 meters apart, this wavelength is 3 meters. This wavelength is 6 meters. So how do I make the wavelength shorter? I make the frequency higher. So what I'm doing is I'm oscillating that more quickly, and when I get to the right pattern, I can get a nice low standing wave. So Brody, I want you to create the third pattern up there. You're going to have to go, my arm's getting tired, so you're going to have to go faster with that frequency to try to get 3 of those loops instead of 1 loop, instead of 2 loops. You need to get 3 of those loops. Are you ready to give it a go? All right, don't let it go. You did it. Nice job. Now you can definitely see some places, keep it going. You can definitely see some places where the slinky doesn't appear to be moving at all. And that's right there at a point where we have destructive interference going on. I see another spot over there that's sort of in front of Gundy there that has destructive interference going on. Of course, if that's destructive interference where the thing doesn't appear to be moving, what kind of interference do you think exists in these really large amplitudes? That'd be constructive interference. Okay, now you ready to try to do 4? Sure. Okay, now instead of it being a vertical, instead of it being a horizontal, what we want to do is we want to do a circular one. So here's what a circular one would look like with a single loop. This is what you want to do, like the jump rope kind of thing. Both of you want to jump rope. This is what it looked like with 2 loops in a sort of a circular kind of waveform. Are you ready to try 4? Yeah, I'm going to let you do that one just a minute. Let it die down. Okay, that's 3. Okay, now you don't need more amplitude. What you need is higher frequency. So what you're doing is you're trying to go with greater energy, but you just need to go more frequent, right? So go ahead and give it a go. 4. It's really tough to get to 4. I mean, you have to be. Now I'm a trained professional, so I'm going to show you. I'm going to show you how to get 4 of those. Are you ready? Okay, you got to be really quick. It's a really fast hand action here. Here we go. Okay. Come on, how do you do it? Do we do it? Is there 4 loops? Yeah. Nice. You want to try to get 5? Oh. You just got to go really frequent. Now, it's probably hard to do that with a circular motion. Try to do it horizontal, you can probably do it. You want to try 5? Cool. What? Horizontal or spinning it? No, spinning is way. Spinning looks cool, but it's really tough to do that. So you got to. There you go. You can do it. You got to get just the right frequency. There's 4 loops. Nice job. Now, if you want to get 5, I'm just going to skip over 5 and go right to 6. I'm going to go over 5. I'm going to go right to 6. Are you ready? I'm going to give it a little bit more room so I can do this. Okay, we're going to try to get 6 of these things. Really quick. How many did I get? Did I get 6 or 7? You got to beat it just right. Oh my gosh! Right. Give Brody a round of applause. Let it go. Let it go. All right. Somewhere on over here, I'm going to show you this on a strobe light. Come on up for a minute. Now, this one I do not want to cause any major issues with you. So please, if you know you have a strobe issue, I don't want you to occur. Okay. Now, first, I'm just going to show you what this looks like without a strobe light. So come on up for a minute. The very first standing wave pattern looks like this. Now, if this, don't get caught all up like that. So the very first standing wave pattern looks like so. We have a node at the endpoint, a node at the endpoint. We have a big antinode in the middle. Now the next standing wave pattern would look like this. And so when I get it to the second standing wave pattern, it would look like this. Come on. Come on. Oh. Okay, so there we go. Nice little standing wave pattern. Can you guys see the loops? Okay, I'm going to try to get the third one. Now the third one, we have to sort of get this thing, give it a little bit of coaxing it a little bit, and you can see that nice little standing wave pattern. Now what I'm going to do is I'm going to hit the lights, and I'm going to try to hit this with a strobe light so we can sort of freeze that motion down. Now I'm going to put this on here to block oh, come on, get back in there. Okay, come on. Get back into that nice little pattern. Okay. Oh, I want you over there. Okay. It's going to get a little scary. Could you go close that window for me, Dawson? David, can you go hit the light inside of that thing there? I'm going to try to make this be dark so that when you guys are viewing this, you're looking at just the strobe light here. So again, I'm going to try to freeze that motion using a strobe action. Okay, now if you've never seen this before, it's actually pretty cool. But you don't want to have the light so it'll go right in your eyes. Now, so what I'm going to try to do is I'm going to try to freeze that motion so you can sort of see that waveform stationary. So what I'm doing here is I'm trying to match the frequency of that oscillation so that wave appears to be stationary. So let's do it a little bit higher frequency. And so it looks like there's a little bit of wobbling going on in there, so it's not a perfect standing wave yet. That battery's not hitting. Okay, I'm just going to do the second standing wave pattern. So again, you can freeze this motion down by using a strobe light to be able to sort of stop its action. Okay? So again, if I can match that frequency just right, then you can see in this case here. In fact, you can sort of see the detail. You guys see the little loop in there in each one of the crests and troughs. There's a little bit of a knot in there. And so what I'm doing there is I'm trying to freeze that motion down. Does that make sense how I'm doing it with the strobe light? The light is hitting it at the exact same frequency as that thing's oscillating, which means that it appears to be stationary. In reality, it's moving pretty quickly, but I'm hitting it once in its cycle each time. Now, if I hit it twice in its cycle each time, you're going to see a waveform that starts to look like this, where I'm hitting it both at the top and at the bottom. It's just a single wave, but I'm hitting it twice in its cycle. I can hit it maybe 3 times in its cycle. And you might see that the rope is being hit 3 times in a cycle. So in reality, it's a nice little standing wave pattern. Could I hit 4 in a cycle? So sure enough, you can sort of see that. Okay, so what did you say? All right, which is why I wanted to show you guys that, right? That's sort of neat to see. Now, you do have to be careful with strobe lights. Do they have strobe lights at dance parties and stuff like that? You guys, do they have the strobes? No? All right. I like it. All right, back to this here. So if you had to watch that, you couldn't watch that thing as a video recording, but nonetheless, we did some pretty interesting things with the strobe light. All right, going back to this. Okay, let's fill in a couple of things on this slide. Again, standing wave patterns. You have to be able to draw them. You have to be able to interpret them. So first of all, let's do these things here. Antinodes are places where we have constructive interference going on. So antinodes are constructive interference. It's where a crest and a trough, a crest and a crest always meet, which makes the amplitude even larger. The nodes are places where there's no motion between, for that. That's where we have destructive interference occurring. Now, I want to show you a couple of videos, or actually this video that I want to show you is just how it gets created with a reflection and an incident wave. So this will probably help you understand it a little bit better. It's hard to draw this, so I'm just going to sort of let the video sort of show you this. We have a continuous wave coming in on the left. It's going to hit that terminal end point, and at this point I have the terminal end being fixed, which means that wave is going to reflect inverted. But it's going to coexist at the exact same place as the incoming wave is. And so what you're going to notice as it hits that endpoint is it's going to reflect in the same place that the red wave is going out. And so you're going to notice the other portion is inverted. That blue portion is riding over the same medium as the red portion. So how these things act, if I were to pause this for a second, you would notice that these things here, that would be like two waves in the exact same spot. So this would be a really large amplitude. This would be a really large amplitude because both of those things are interfering with each other. If I were to continue this, you would notice that the black portion would then represent what the standing wave would actually be. And so we wouldn't see the red, we wouldn't see the blue. What we would see is just the black portion. And so standing waves are where we have an incident and a reflected wave sort of interfering with each other. Okay, and so that's what a standing wave would look like. Now, we need to be able to draw and interpret what's going on here. So let's go ahead. You're going to have to do a little bit of math here. Brody, you and I started with a really low frequency oscillation to be able to get that first pattern. Let's say that we oscillated up and down twice every second, so 2 hertz. I need to be able to look at this. If this is a 6 meter distance, if that's 6 meters in length, then I should be able to look at this diagram and say that that wavelength is 12 meters. And that's again because I need 2 of those loops, if you will, to be a full wave. So if the velocity is equal to frequency times wavelength, I simply take that 2 hertz, which is the frequency at which we are oscillating at, multiply that by 12 meters, and I get the speed of that wave is about 24 meters per second. Again, the speed of that wave depends on the material properties. So what's the tension in that rope? How much mass do I have in that rope or that slinky? That determines the speed. And of course, if I want to get that standing wave pattern set up, I need to oscillate it at a particular frequency. Now, what I'd like to do is calculate the frequency needed to get this to oscillate in the second mode. Well, if this is 6 meters, then I look at this pattern and I see that that is 1 full wave. I would say the wavelength of that standing wave is now 6 meters. So the wavelength has been cut in half. If I want to determine that frequency, I'm going to use that frequency as equal to velocity divided by wavelength. The velocity is still 24 meters per second, but now the wavelength is 6 meters. When I do 24 divided by 6, I get 4 hertz. So in order to get the first standing wave, I needed to cycle it at 2 cycles per second. To get the next standing wave, I needed 4 cycles per second. Let's do the last one. If this distance is 6 meters, if this is 6 meters, then I need to be able to look at this standing wave pattern to determine the wavelength. And you might notice that a full wave spans 2/3 of that entire length. So if this is 6 meters, this would be 4 meters. The wavelength there would be a 4-meter wavelength. You notice that each time I increase that frequency, I'm making that wavelength shorter. If I wanted to determine the frequency, I would take the velocity divided by the wavelength. It's still 24 meters per second. That depends on the speed at which the wave propagates along that medium. I'm not changing the medium. That's still going to be the same medium as before. The wavelength has shortened to 4 meters, and 24 divided by 4 is 6. And what I notice here is that the frequency seems to be going up by the same amount every time. 2 hertz, then 4 hertz, then 6 hertz. Let's say I wanted to create, just as a standing wave, let's say I wanted to create that. What frequency would I need to be able to get that one? So if that's the next standing wave, do you guys agree that I would need 8 hertz for that? Every time I go to the next standing wave, I go up by 2 hertz. So if I wanted to get one with 5 loops in there, that would require 1, 2, 3, 4, 5. That would require 10 hertz. The idea there is that every time I go and increase that frequency by that 2 hertz, what I'm doing is I'm getting the next standing wave pattern. Okay. Important idea related to standing waves. I'm going to go ahead and stop with that. I have a short little